Well, hello again. In this example, you will learn how to incorporate floor live load reductions when sketching load diagrams for beams and columns within a building. Specifically, we will take a look at this framing system made of beams, girders, and columns. We are told that the unreduced live load on this floor system is 40 pounds per square foot. We're being asked to sketch the reduced live load diagrams for beam B1 and girder G1. We are also being asked to include column B3, which is this one right here. Now, one of the things that we have to know when computing live load reductions is we need to know how many floors the structural element is supporting. What we find here is that even our columns are only supporting one floor system. So let's make sure we understand the framing system here. If this bay size is 30 feet, and if you count, there's 1, 2, 3, 4, 5, 6 spaces, that will then make the beam spacing to be 5 feet on center. We also want to acknowledge that the slab behavior is going to be one way, and that will help us to get the diagrams that we need. The live load reduction factor as given by ASCE 7 says that the live load can be taken by multiplying L naught, which is the unreduced live load, by this particular reduction factor, which is computed as 0.25 plus 15 over the square root of KLL, and that's multiplied by the tributary area. And what we are told is that if it's supporting only one story, that factor right here must be greater than or equal to 0.5. We're also told that our load is reducible if our KLL AT quantity is greater than or equal to 400 feet squared. So I've provided a table here showing the KLL factors for some typical structural elements. Of concern is an interior column, so column B3, and it says that we have a KLL factor of 4, and we will use that a little bit later. We're also looking at our particular beams and columns, beam B1 and girder G1. Both of those are interior type beams, and those will have KLL factors of 2. So let's start looking at beam B1. What this is going to require is we are going to need the tributary area for beam B1. In order to do that, we will draw dividing lines halfway between the beams. So there and there, and this then identifies the tributary area for that particular beam. We've already decided that those are a spacing of 5 feet, and that tributary area has a length of 45 feet. So let's go ahead and compute that. 45 feet multiplied by 5 feet, and this will give us a tributary area of 225 feet squared. Now, in order to find out if this is reducible, we need to compute the KLL AT factor. You will recall the KLL factor for the beam was 2. And so that total quantity is 450 feet squared, which incidentally is greater than the 400 feet squared, which then says that we are reducible. Now, while we are here, let's go ahead and note we have a beam length of 45 feet, and since the tributary area is uniform along the entire length of the beam, it will produce a uniformly distributed load. And our task is going to be to identify what that magnitude is. So we want to go ahead and compute the reduction factor for this. 0.25 plus 15 over the square root of KLLAT, which we've already found out to be 450 feet squared, and this will be 0.957, which is greater than that 0.5 threshold, so we will consider this to be an okay reduction. So the new live load that we will be using is 0.957 multiplied by the 40 pounds per square foot. And so we can use a 38.3 pounds per square foot for this particular beam. So W for the beam is 38.3 pounds per square foot multiplied by the tributary width to that beam, which is 5 feet, and that will give us 191.5 pounds per linear foot. What we can do is we can come back here and go ahead and label that 191.5 pounds per linear foot. Moving on to the girder now, we will recognize that the beams will rest on the girders, and thus they will provide point loads to the girders. So we know we're going to have a point load coming down at every location where there is a beam. Based on our knowledge of the spacing of the beams, we know that each of those point loads is going to be here at a 5-foot spacing. And you can very quickly see that this will indeed produce a 30-foot span. Of course, we need to come up with what the reduced live load is for each of these point loads. This can be a little bit tricky. We've got to make sure that things are clear in our own mind. So for a single point load, this is what you're going to do. You're going to draw dividing lines halfway down, and this is halfway down the beams. Okay, because remember, the load goes from the slab to the beams and then to the girders. So if this lines that I just sketched delineate the tributary width to the beam, then half of that will go to one end of the beam and the other half will go to the other end of the beam. So girder G1 receives the area that I just shaded in. And then of course we have a beam on the other side, and half of that will go to girder G1 as well. And so that overall length right there is 45 feet. It gives 22.5 feet from each side. And of course, this is 5 feet. Okay, now this would be the tributary area to the girder, but of a single beam. Let's go ahead and actually compute that. 45 feet times 5 feet, we've seen this before, as being 225 feet squared. Okay, now this is on a per beam basis. What we need to do is we need to look at this as what total area is going to the girder. And so you'll notice that we have 5 locations where those beams are coming down. And so we know we've got, this is for the one beam, but it will include for all of those beams, this is going to be your total. And in order to get the live load reduction factor, we need to use the total tributary area going to the girder. And then later, to get the specific point load quantity, we will use the tributary area to each particular point load. So the AT, tributary area, per girder, is equal to 225 feet squared, and then we have 5 point loads. And that will equal 1125 feet squared. Let me come back here and just write that. Now we can check our KLL AT value, 1125 feet squared multiplied by 2, that's the KLL for a beam. That'll give us 2250 feet squared, which of course is greater than the 400 feet squared. So we know that this is reducible. Okay, so let's go ahead and compute that reduction factor. 0.25 plus 15 over the square root of 2250. This equals 0.566, which is greater than the 0.5, so we are okay on that. So now we can compute what the reduced live load is going to be. That's the 40 pounds per square foot multiplied by 0.566. That will equal 22.6 PSF. And so per point, we can calculate what that point load is, being 22.6 pounds per square foot, times the tributary area for each point, 225 feet squared, gives us 5,085 pounds, or approximately 5.1 kips. And we can now come back and draw it on our diagram. To finish this example out, we still need to look at the load that is on column B3. I'm going to delineate the column lines. Column lines are the lines where the columns are located. And to get the tributary area for that, we will draw dividing lines halfway between the column lines. The tributary area for column B3 is delineated by those lines. We are 30 feet here and 45 feet here, giving us an AT equal to 45 feet times 30 feet, 1350 feet squared. KLLAT is equal to, and for a column, we already noted that the KLL factor is 4, so 1350, which is 5,400 feet squared. Of course, that is much greater than the 400 feet squared required, so this is reducible. We can now go ahead and get our reduction factor calculated. 0.25 plus 15 divided by the square root of 5,400 is equal to 0.454. Now this is actually less than the 0.5 that is allowed. So what we will do is we will go ahead and use 0.5 for our reduction factor. So the live load is calculated as the 40 pounds per square foot. We will use that 0.5 reduction factor. That gives us 20 pounds per square foot. And the total load going down on that column, 20 pounds per square foot, multiplied by the tributary area. And there you go. It will compute out to be 27,000 pounds, which is 27 kips. And that concludes this example. As always, it's another beautiful day for studying structures.